Hello everybody, and welcome back to another Big Ideas lesson. Today we're going to be talking about lesson 1.1. This is where it kind of all begins here for Algebra 2. Much of what we do in the first semester is based on the fundamentals talked about in this lesson. In this lesson, our main objective is to learn about what we call parent functions and how we can transform those parent functions to make pretty much any graph that we want, at least of those forms. Before we get started, let's talk a little bit about what a parent function is. When we say a parent function, we just mean the most basic form of a function. The most basic form of a function. When we're doing math, we are able to have a wide variety of different graphs to represent the same functions. For instance, I could have a straight line, or I could have a straight line that's slightly tilted, or a straight line that's slightly up and tilted. There's a bunch of different things that we can do to equations. With these graphs, we want to make sure that we have a baseline for them. Let me give you a quick example. Here, on this graph, we have three different parabolas. It's kind of hard to tell with the colors, but we have a blue one, we have a red one, and we have a green one off to the side. All of them are slightly different. Some of them are slightly thinner than the others, some of them are slightly to the right of the others, but the one thing they have in common is they're all parabolas. Their parent function is called a quadratic. At the bottom of your page here, we actually have all four parent functions that we'll need to keep in mind for this semester. We're going to be working with all four of these interchangeably. We're not going to spend a whole unit on absolute value and a whole unit on linear and a whole unit on quadratics. We're not going to be doing that necessarily. Our goal for this semester is to look at these parent functions and realize that we can give them very similar treatments. We're going to talk about those treatments in a moment, but I want to just mention the four basic parent functions. The first one we have here is a constant function, and you can see what that function might look like here. When f of x just equals some number by itself, we get this straight line going across the graph. The key with this is it has to be a straight horizontal line in order to be a constant function. Let me give you a couple examples of constant functions here. If we take a look here, the blue line is what we call our parent function. Why is it called the parent function? Because it's at y equals 1. It's at 1. We said here that f of x should equal 1. One trick to keep in mind is that f of x is almost interchangeable with the letter y. We use f of x to denote a function. F of x just means, hey, this is a function of x. We're doing something to x values to get 1. That's all it means to be a function. It means we're doing something to x values. You can also see on the graph, I have a couple different lines. I have a red line and a green line. According to the graph, the red line is at y equals 3, so it's a little bit higher than our parent function. As for the green line, it's a little bit lower than our parent function at negative 3. We call these changes transformations. Up here where it says transformation, a transformation is something that changes the size, the shape, or the orientation of a graph. Something that changes the size, shape, or orientation of a graph. So in my graphing calculator, we have a couple of transformations here. Let me make it a little bit brighter. We have a couple of transformations here. We start with the blue line. It seems like one of our transformations went up 2. And another one of our transformations went down 4. We have a name for this. What we're doing is we're basically sliding our graphs up and down, right? Well, the name we have for this sort of slide is translation. Translation just means that we are sliding our graph in certain directions. Like in this case, how we moved it up and down. A transformation is just another name for a slide. We can slide or shift our graph up or down or left or right. But any direction we slide it, it's considered a translation. So that might be one of the examples we see of a transformation. Let's talk about the next parent function. The next parent function is the linear function. Linear. When you hear the word linear, what do you think of? I don't know about you, but it makes me think of a straight line. Linear means line. So whenever you graph it, you're going to get a straight line like this. It's a little different than the constant, but it's a line that has a slope. Let me give you a couple more examples real quickly. So if I take a look at these three graphs right here, all three of these are linear. Our blue line is the parent function. You can see up here the equation is just y1 equals x, or f of x equals x, because they're interchangeable. I moved the red line a little bit to the left, about 3 units. So if I go and see what that red line should be, the red line equation is y2 equals x plus 3. So it seems like we had a little bit of a change here. Instead of f of x equals x, we have x plus 3, and that moved it left a little bit. Finally, the green line I have as 1/2 of x. So all of these are different changes of these graphs. The next parent function we have here is the absolute value function. This is something that you may have touched on before. You may have touched on this in your Algebra 1 classes, but we never go too in depth with them. The absolute value function is a function that looks a little bit like a V, and anytime you see a V-shaped function, you should know, hey, that's going to be my absolute value function. A couple things about the absolute value function. The absolute value function is always going to look the exact same on the left as on the right. It's going to be perfectly the same on both sides. Up on my graph here, I have 2 examples of the absolute value function. The blue one is our default absolute value of x. But you can also, just like the other ones, translate it right, left, up, and down. So this one is translated to the right 5 units. If I take a look at 5, for instance, we can see right there is where the dot is. Right there is where the bottom is. So I've moved this one right 5 units. There is something else that we can do with these, though. Give me a moment to type in these new equations. And done. What I've done here is I have just graphed our normal x minus 5 here, but I've done a couple of quick changes to it. Let's watch these changes in action. Interesting. What I've done is I've taken this blue graph and I have flipped it over the y-axis to make the red one. It's sort of like a mirror. I've mirrored it over that side. Beyond that, I also have this black line down here. It looks like I've just taken the blue line and flipped it over the x-axis. A flip is another type of transformation that we can have with these functions. And the word for it is called a reflection, just like a mirror. A reflection is just another word for a flip. So, a reflection is when we flip our graph over some axis. Well, if we take a look at these graphs, right, it looks like to get from the blue line to the red line, I just flipped it over this vertical line, the y-axis. So that's a reflection because I flipped it over the y-axis. For the black one, I flipped it over the x-axis. You can imagine how I've taken what I have up top here and flipped it over this horizontal line so that it's upside down. That's another transformation, is a reflection. Last but not least, we have our final parent function, the quadratic. The quadratic is something that we're very familiar with from Algebra 1. You may know it as a parabola. A parabola is that weird shape we get that looks sort of like a U. So, of course, we can also transform this parabola in the same ways we did with the other ones. Here, I've got 3 equations for parabolas. Let's see what happens. So our basic parabola is in the blue. Our red is translated downwards, and our black one is upside down. It's been flipped or reflected. So all of these transformations work for all of these parent functions. They're all the same. In future lessons, we're going to talk about how to achieve this, but there is one more transformation I want to show you. Watch what happens if I put a 5 in front of my x squared, and watch what happens when I put a 1 over 5 in front of my x squared. Let's see what these 3 graphs might look like. As always, our blue is our parent function, but the red one is very skinny, and the black one is much more wide. These transformations are called vertical stretches and vertical shrinks. We can think of a vertical stretch or a vertical shrink as a dilation. You know when your pupils dilate and they get either really big or really small? Well, just like how the pupils in your eyes might dilate, our graphs can also get much bigger or smaller. When we talk about a vertical stretch, the way I always like to think of it is this. Imagine in between my hands I have like a ball of taffy or a ball of gum, and I am pulling on it. I'm pulling on it up and down. That's a vertical stretch because I'm stretching it in a vertical direction. When you stretch a piece of gum in a vertical direction like that, as it gets taller and taller, it also gets thinner and thinner and thinner. It gets skinnier and taller. That's kind of what happened with our red graph here. It got skinnier, it got pulled in, but it's also getting much taller. We just can't see it because we would have to look up and up and up to see it. A vertical stretch happens when we say something called our stretch factor. Our stretch factor is bigger than 1. Stretch factor is a word I'm using in place of a different word. We're going to talk about the different words we can use to describe vertical stretches and vertical shrinks in a different lesson. But the main idea is vertical stretches are what happens when we have some number greater than 1 affecting our graph in certain ways. You might be able to even tell how it affected our last graph. However, we also have something called vertical shrinks as well. Vertical shrinks are when our stretch factor is between 0 and 1. Our stretch factor is between 0 and 1. Again, we'll talk more about what this means in 1.2 as well as in 2.1. Let's do a couple of quick practices. If we flip over to the next page, to page number 5, where it says extra practice, we've got some identification to do. We're asked to first of all identify the function family to which f belongs. We want to pick out what each of the parent functions is for these 4. Try that out. Try writing down what the parent functions are for each of them by pausing the video and come back in about a minute or so. Hopefully we had a chance to pause the video and try these out. Let's take a look. This graph is linear. If we compare it to the parent function for linear, we see a diagonal straight line and a diagonal straight line here. You want to know how else we can tell it's linear? The linear parent function is f of x equals x. So if we have just an x all by itself in our equation, we'll know that it should also be linear. And lo and behold, here it is. Just x with nothing crazy done to it. It's not being squared, it's not being absolute valued, it's just x. This one right here is the constant function because it goes from side to side, and also the constant function is when f of x equals a number. This one here is the absolute value. This is absolute value. You can tell from the v shape and also from the absolute value sign in the equation. And this weird one is going to be the quadratic because the shape is a parabola and we see an x with a squared on it in the equation. That squared tells us it's quadratic. Now here's the problem. It wants us to compare the graph of f to its parent function. For this, we need to ask ourselves, how do we get from the parent function of these graphs? So for instance, from the parent function here of x to this. Well, it looks like a couple of things happen, right? First things first, our graph is moved way up. It is moved up 8 spaces. So we could say that there is a translation 8 units up, because that means it slides 8 units up. You can tell that from the equation with the plus 8, but you can also tell it just by looking at the graph. This point is 8 units up. Next off, notice how it gets a little bit less stretched vertically. Our line goes from being like this to suddenly it's almost like we're being pressed down vertically. We can call that a vertical shrink. Vertical shrink happens when we're getting less tall, when we're getting shorter, closer to being a straight line. So we say this is a vertical shrink. And remember how I said we have a growth factor in between 0 and 1? This number right here is our growth factor. It's the 1/4. So we can say it's a vertical shrink by a factor of 1/4. Last but not least, notice how this graph goes from going up and to the right to down and to the right. It's almost like we took it and flipped it over the y-axis. Can we see how that might have happened? If we flip this over the y-axis, your new graph will look exactly the same, just mirrored. So it goes from being this to being this. So we can say that this one was also reflected over the y-axis. Very nice. Down here, we are asked to graph the function and its parent function. If you have a graphing calculator, this can be very, very easy to do. I want to show you how to do it with a calculator, but I also want to show you how to do it without one. If you have a graphing calculator, let's plug in the regular parent function for this. So first of all, what's the parent function of number 5? It should just be a straight line. It should be linear because we only have an x here. So the parent function is f of x, or in this case y1, equals x. The transformed function is x minus 7. You can graph these on the same line if you want to help inform how you should graph it on yours, but you can also click on the second button and then the table button to access a table of values. I always recommend having some negative values and some positive values to help you graph these functions. For instance, when x is -4, our original is at -4. So our original graph, I'm going to graph it in blue, has a point here. When it's at -2, it's at -2. When it's at 0, it's at 0. When it's at 2, it's at 2. And we can see what our original parent function should look like. It should be a straight line going in this general direction. Apologize for my shaky hands. There we go. That's the parent function. That's y1. If I want to take a look at y2, it's a little bit tougher to graph. We need to find some values that will actually fit on the graph. Things like, for instance, -1, -8. So if I take a look, -1 should be right around here, -8 is right here, so we get a point like so. Or like 0, -7. If I'm at 0, that means I'm on the y-axis. -7 is right here. Or you could use any other point. You could use a point like 4, -3. So I can go down here and get a point. The table just helps you find some points to graph. And as long as you have at least 2 points, though the more the merrier, you will be able to figure out what this graph should look like. If I was to continue this graph up, it would continue to look like this. This is the transformed function. So f of x equals x minus 7 is this red line. Let me actually write that down. And I'll use b of x. Why not? For the blue line. What is the transformation here? What has to happen in order to get from the blue line to the red line? Many people's first instinct is to say, we move down 7. Think about it. We go from 0, 0 to 0, -7. That's what happened according to our table. We could say the transformation is a translation 7 units down, or down 7 units. However, those keen-eyed among us may realize that this is not the only transformation we can see. Sure, maybe it moved down 7 and that's how we got our final answer. What if it didn't? If we take a look at these points, for instance, could we also say that it moves to the right a little bit? Instead of moving down to get to the red line, could we just say that the graphs moved to the right? We could. These lines continue on forever. So we could say that the line moved to the right as well. Either one of these, a translation 7 units down or a translation 7 units right, both of them are valid interpretations of the transformation. Either it moved 7 units down, or we could think of it as moving 7 units to the right. Both are valid for this problem. Last but not least, I'd like you to turn the page and take a look at problem number 12. For problem number 12, we have a table here, table of values. The table shows the distance a biker rides in his first team relay competition. And we're trying to figure out what type of function we can use to model the data. In other words, what parent function we can use. Keep in mind, we have 4 options. We could say it's constant, we could say it's linear, we could say it is absolute value, or we could say it's quadratic. One of these is really easy to immediately eliminate. The constant function. Remember, the constant function is a straight line. It means that as x goes up, our y value never changes. It stays constant. So we're not dealing with a constant function here. If we take a look at a quadratic function, once again in our calculator, for instance, let's take a look at x squared. We see that as x goes up, our y increases by more and more every time. You can tell something is a quadratic if and only if you can see it go up by squaring the variables. Let's take a look here. 1 to 1, 2 to 4, 3 to 9, 4 to 16. As we go up, the amount it goes up by increases every time. To get from 0 to 1 is just 1 away. To get from 1 to 4, it's 3 away. To get from 4 to 9, it's 5 away. To get from 9 to 16, it's 7 away. Is that what's happening in our table here? Are we going up by more and more every time? No, we're not. We're going up by the same amount every single time. So it's definitely not quadratic. Finally, there's nothing to tell us that it isn't absolute value, but if we take a look at what the absolute value means, it means that, in general, we have a V-shaped graph. A V-shaped graph happens when you have some sort of reflection in your table. If I was to go back to the calculator, for instance, and type in the absolute value of x, graph it, and make a table using that second button, you'll see that, whoops, I apologize, you'll see that the values in the table go up in both directions. And we're not really seeing that here. We're not really seeing that going up in both directions. The reason is we don't have negative hours to take a look at. So in this case, the absolute value function wouldn't be the best to model the data. Anytime your function goes up by the same amount or down by the same amount every time, in this case we're just adding 12 every single time, we say that is linear. So this is linear. And our explanation is because we're going up by the same amount every time. If the biker's teammate rides at the same pace, but leaves 1 hour later, what type of transformation does this represent? Oh boy, this is a little bit tricky. Let's take a look at the table here, for instance. So originally, we have the following. We have our time up here, and we have our distance up here. So when we reach x hours, we'll go to y distances. After 1 hour, we said we go 12. After 2 hours, we said we go 24. After 3 hours, we said we go 36. After 4 hours, we said we go 48. This is just the table from up above. But let's add another row to this table. Let's think about the distance of our friend, or our teammate. If they ride at the same pace, but leave 1 hour later, where will they be after 1 hour? Well, if they're leaving 1 hour later, we can think of them as sort of chilling out at the starting line, right? After 1 hour, they'll still be at 0. They won't have moved. But then they're going at the same pace, so they go up by 12 every single time. Interesting, right? It's kind of strange to see what this transformation might be. If I was to graph our original function here on a table, going from 1 to 12, 2 to 24, 3 to 36, 4 to 48, it might look something like this. Something like this here. So if I go to x equals 1, for instance, you can see I'm typing in 1 here, I'm at 12. If I go to x equals 2, I'm at 24. If I go to x equals 3, I'm at 36. This is what our original graph might look like. But we want it so that instead of being at being at 12 when we're at 1, we want it to be at 0 when we're at 1. If we are at 0 when our graph is at x equals 1, you can almost imagine it being to the right slightly. In fact, if I type this out real quick here, give me a moment. And if I was to graph it, it might look something more like this, right? Because at a time of 1, they're still at 0. They're still on the x-axis. So if we compare these two, let's take a look. Oops. When x is 1 on the red line, we're at y equals 0. When we're looking at the blue line, for instance, when we were looking at the blue line, we were already at 12. So it looks like this transformation is just moving it 1 unit to the right. This transformation is a translation 1 unit to the right. Translation 1 unit right. That's it for these notes, everybody. Thank you so much for listening, and I hope you have a fantastic rest of your day.